In this section, we're going to look at certain kinds of prime numbers. Last time I tried to indicate that the number of primes that exist is infinite. There's no end to them. So far, here's the primes that we've been looking at. I did 2, 3, 5, 7, 9 is not prime, 11, 13, 17, 19, 23, etc. And we went all the way up to 97. So I was just showing how to get the primes up to 100, and 97 was the last prime before 100. So now we're going to use these primes to make bigger primes. Let me show you how we can do it. Look at the number 2 plus 1. That equals 3, which is a prime number. Now check this out. If I do 2 times 3 plus 1, so I did the product of the first two primes and then added 1 to it, I get 6 plus 1, which is 7, and that's prime. Continue on. How about 2 times 3 times 5 plus 1? So now it's the product of the first 3 primes plus 1. In this case, we get 211. Is that prime? Well, let's check it out. First thing you would do is try the square root of 211. Let's see what that is. So I'll access my square root. 211. It's about 14 and a half, so I'll just say about 14. So what we need to do is try the following prime numbers to see if they'll go into 211. 5, 7, 11, 13. Those are all the prime numbers less than or equal to 14. And so I'll try each of those to see if they go into them. Now hopefully you can see that 2 is not going to divide evenly into 211. We can also throw away 3, because if you add the digits 2 plus 1 plus 1, that equals 4, and that's not divisible by 3. So I can cancel out the 3. 5 is easy because the number itself does not end in a 0 or a 5. 7, now 7 I'll have to try. So let's bring out the calculator. Try 211 divided by 7. And I have a decimal there, so that means that there will be a remainder when I divide by 7. Let me move this thing around. Try 11. 211 divided by 11. I should probably fix that and make it actually 11. If you hit your up arrow, it will allow you to go back to the problem at hand. Now if I hit enter, it will allow me to go and fix it. And we can see there's a decimal there, so 11 does not go into 211 evenly. And then finally 13. 211 divided by 13. 16 point something. So that tells me that in all cases we have some sort of remainder if we divide by any of those numbers. So 211 is in fact prime. You can do this all day long. I'll go next. 2 times 3 times 5 times 7 plus 1. Here we're going to have 2,311. Now, do I check for primeness? Of course. I'll take the square root of 2311, and that will be approximately 48 point something. What that means is that we would have to try all the prime numbers up to 48. And they go on and on and on. I think the last one before 48 is 47. So you try all of those, and I'll tell you what, you're going to get some sort of a decimal every time. So this is a prime. So what we have here is we have a way of creating new prime numbers from the old ones. Here's how we do it. we can do 2 times 3 times 5 times 7 and keep going till some prime number, as long as you go up to in order. And then if you add 1 to it, this number that you create will always be prime. And in this way, you can keep creating bigger and bigger primes no matter what. So this is one way to see that you're going to have an infinite number of them. For example, if you thought if P was the largest prime, so if we have P as the largest possible prime, then this thing that I created, 2 times 3 times 5 times all the way up to that number P plus 1 is a prime number, and it's bigger than P. So you can't have a largest prime number. So bigger than P and prime. So in this section, we're going to be just looking at a few specific types of primes that were studied historically. Let me show you another type. Take any number and divide it by 4. Let's say any natural number. What are the possible remainders? We can have the number 4 could go into the number evenly, so we could have a 0 remainder. You could have a remainder of 1, 2, or 3. So those are the only 4 remainders that are possible when you divide by 4. So what happens when you divide by 4? Let's say you take a number here. N is my natural number, and I divide it by 4. Let's say the remainder is 3, for example. So what's going to happen is I'm going to equal k 0.75. 0.75 is 3/4, so I know that the remainder is 3. Well, what I'm going to do then is I'm going to take that k plus 0.75. So k is a natural number, 0.75 is the decimal port. I'm going to multiply both sides by 4. Now, you probably remember the distributive property. I take this 4 and multiply to each component inside of the parentheses. So we end up with 4k. Now 4 times 0.75 is equal to 3. So the number itself can be written in the form 4k plus 3. In fact, every natural number can be written in one of the following ways. So we could have numbers like this, 4k, these are multiples of 4. We could have 4k plus 1. The numbers, when you divide them by 4, leave a remainder of 1. 4k plus 2. Numbers that when you divide them by 4 have a remainder of 2. And then finally 4k plus 3. Numbers when you divide them by 4 have a remainder of 3. So any natural number can be written in one of these forms. So what are we going to do with that information? Well, historically, numbers of these forms were looked at for primes, whether they could generate primes or whether they contain primes, and we're going to take a look at a few of them. As an example, find 3 primes of the form 4k plus 3. Well, let's start with k equals 0, as simple as it gets. 4 times 0 plus 3 equals 3, and that is indeed a prime. How about k equals 1? We have 4 times 1 plus 3. That equals 7, which is prime. How about k equals 2? 4 times 2 plus 3 equals 11. That's prime. So I've already done it. I've already done what the problem has asked me to do. Is this going to work forever? Well, let's try the next one. K equals 3. 4 times 3 plus 3. That's 12 plus 3 is 15. That is not prime. Historically, people tried to find primes of various forms. That means they thought maybe there might be a formula for them. So they tried different things like this 4k plus 3 business, and after a while they found out it doesn't always work. So they investigated those. Then what about these ones? Then we have ones like this 4k plus 1. These are guaranteed also to be all odd numbers, just like 4k plus 3. It turns out, watch this, has an interesting form though, even though it may not always be prime. Let me say, try k equals 0. We get 4 times 0 plus 1 is 1. That really doesn't count much for anything, but I could think of it as 0 squared plus 1 squared. So many of these, while in the search for prime numbers, interesting other properties were discovered along the way. Check out k equals 1. 4 times 1 plus 1 equals 5. That's a prime number, but check this out. I can do this with it. That's 1 squared plus 2 squared. K equals 2. 4 times 2 plus 1, that's 9. That's not a prime. And guess what? I cannot write 9 as a sum of 2 squares. So this is an interesting property. Whenever I get one of these numbers of this form, let's try 4 times 3 plus 1. That's 13. That's a prime number. Whenever it's prime, you can also take it and write it as a sum of 2 squares. Here's 2 squared plus 3 squared. Very interesting property. So when 4k plus 1 happens to be prime, it can also be written as a sum of 2 squares, as I demonstrated in this previous example. There's a whole collection of prime type numbers that are assigned to individuals. One such individual, his name was Mersenne, and so he, of course, looked at certain numbers to see if they were prime. Here's what he did. He let m sub n, that n is a subscript, equal 2 raised to the n power minus 1. He investigated when, or for what numbers n is that thing a prime. So let's start with n equals 0. We have m0 then is 2 to the 0 minus 1. Well, that's equal to 1 minus 1, and that's 0. So that really doesn't do much for us. Let's go up a little bit higher. N equals 1. M1 equals 2 to the 1 minus 1. 2 minus 1 is 1. Once again, uninteresting. N equals 2. M sub 2. 2 to the second power minus 1. 4 minus 1 equals 3. And there we have ourselves a prime. Finally, for n equals 2. N equals 3. m sub 3 equals 2 to the third minus 1. 8 minus 1 is 7. That is, of course, prime. And n equals 4, m sub 4, 2 to the fourth minus 1. That's 16 minus 1, which is 15, and that is not prime. So in these historical efforts, they would usually come up with something that seemed like a formula. They would test it for a while, and they'd find it would generate a bunch of primes, but then there was always something, no matter what, that showed that the formula wouldn't work. So in fact, there is no known formula that can produce primes, and only primes. This is an interesting property, though. If n is composite, then so is m sub n. That's an interesting property. If you look, take a look here, n equals 4. 4 is composite, and this number here is composite. It doesn't work the other way, though. If n is a prime number, this is not guaranteed to be prime. When m sub n happens to be prime, we call it a Mersenne prime. Fermat took Mersenne's method and expanded on it. So Fermat's numbers then look like this. 2 raised to the 2 to the n. So the n is an exponent on top of an exponent, plus 1. Let's do a few of these so that you can see how they're calculated. So for n equals 0, we have 2 to the 2 to the 0. So this will be f sub 0. Now 2 to the 2 to the 0 is 2 to the 1 power plus 1, because 2 to the 0 is equal to 1. And this, of course, equals 3, which is prime. So it works for n equals 0, n equals 1, f sub 1 equals 2 to the 2 to the 1 plus 1. That's 2 raised to the second power plus 1. That's equal to 5, which is prime. N equals 2. F sub 2, 2 to the second plus 1. Now when you're evaluating these things, you need to do the exponent first. So I'm going to do 2, and it'll be raised to the 4th power. So we have 2 to the 4th plus 1. 2 to the 4th is 16, so that this is 17, and it's prime. You can see this is working well. Let's keep going. N equals 3. F sub 3 equals 2 to the 2 to the 3 plus 1. This is 2 raised to the 8th power plus 1. This equals 257. Is that number prime? Well, to test it, let's check. I'll first take the square root of 257 using my calculator, and we'll find that it's roughly 16. So I have to test the primes 2, 3, 5, 7, 11, 13, and that's all I have to, because the next one is 15, and that 17 is bigger than 16. So I have to try each of these. Now, as before, I can easily toss away 2 because the number is odd. 3 will not go into it. Let's check and add up the digits. 2 plus 5 is 7, plus 7 more is 14. 3 doesn't go into that. The number doesn't end in a 5 or a 0. So then we have these numbers to try. 257 divided by 7, remainder. 257 divided by 11, remainder. 257 divided by 13, remainder. So in fact, 257 is prime. As I mentioned, these things always fail at some point. But this one has been working for a while. If we try n equals 4, my f sub 4 equals 2 to the 2 to the 4 plus 1. That's 2 to the 16th plus 1. This number is 65,537. I won't go through the effort of showing you this, but it, in fact, is prime. It's not till we get to the next number, n equals 5. So I have f sub 5. That equals 2 to the 2 to the 5 plus 1. That's 2 raised to the 32nd power plus 1. And this number turns out to be 4 billion, 294,967,297. This one is not prime. Polynomial primes. A couple of them that the book talks about. We have the Euler polynomials. They look like this. E sub n equals n squared minus n plus 41. And then we have this person's name I never heard of before, Escott. I'll use the letter S. S sub n equals n squared minus 79n plus 1601. And as before, if you look at E0, you're going to get 0 squared minus 0 plus 41. That's a prime. E1 equals 1 squared minus 1 plus 41. Well, that is also a prime. E sub 2 equals 2 squared minus 2 plus 41. That equals 4 minus 2 plus 41. And that equals 43, which is prime. In fact, this produces primes all the way up to 40. So E sub n is prime for n equals, it even worked for 0, didn't it? It did work for 0. N equals 0, 1, 2, up to 40. What happens at 41? Well, E41 equals 41 squared minus 41 plus 41. As you can see, negative 41 and 41 cancel, and we're left with 41 squared, which is 41 times 41. That means that we are not prime. And with Scott ones, we have Sn equals n squared minus 79n plus 1601 is prime for n equals, I don't know about 0, but 1, 2, up to 79. It fails when n equals 80. S sub 80 is not prime. In fact, you should be able to see too that if I plugged in 1601 for n, I would have 1601 attached to each piece, and I could factor out the 1601. Watch. S sub 1601 equals 1601 squared minus 79 times 1601 plus 1601. I'm going to distribute a 1601 from each and every piece. And then if I want, let me add up these numbers. I'm going to get 3202 minus 79. So I'm probably just 1601 minus, where's my minus? 79 plus 1601, enter, 3123. So you can see that at the very least that is a composite. So none of these polynomial formulas always produce primes, but they do produce primes, at least initially.